Hello, welcome back. I hope you're all enjoying your learning and going through the previous days and sessions concepts, and you're getting yourselves familiar about different peripherals and different registers that you're going to use in your projects, and also different concepts as you're progressing along. And I'm happy and I'm so excited to welcome you back. And today is day 12. Please join in to learn what day 12 unfolds you. This is Embedded System Design on ARM Cortex M4 series. Day 12. We are on the intermediate part of the course, so you would get to learn more in-depth concepts. So I'm sure you are more excited as I am. Today, you're going to learn about linker scripts. You're going to get a better understanding about what is linker scripts, and you're going to learn all about it. These are all the sections you would learn today. First, we start with what is a linker and what is a linker script and how does it work in terms of programming and how that is used in the IDE. So all those things you will get to learn. And then you will learn about different linker script commands. There are a few commands that you have to use in the linker scripts, which is very vital, and you will learn that. And also you're going to learn about what is a location counter and what is it used for and how that location counter is referred in the linker description scripts. And then you will go through line by line about the linker file, what it is all about, so that you'll get a more familiar understanding about the linker file. Like in the previous session, the startup file and the linker description file are two most important things that any embedded system design engineer should be aware of and know of, because once you know these two concepts, you can go and modify these two files and you can use it in your own projects. So you can write your own, from the previous session, you can write your own startup file. Likewise, after at the end of the today's session, you can go and modify and write your own linker script. In bigger projects, if they have much resources, for example, if they have a few engineers, in some projects, I also worked in some projects where the engineers only concentrate on designing these linker scripts and also designing the startup file from previous session. So please pay more attention, and you will get everything that you want to know about linker scripts. Before jumping into learning about linker scripts, I would like to tell you a little bit about whom I am representing. I'm representing A2DG. As you can see, it's a startup by Anbukarsu brothers, my brother Alex and myself Arul in 2023. Both of us gathered over 20 years of experience in the industry, and we would really like to share that experience and the knowledge and our journey, what we went through, to you all out there, so you can also get to learn and be tuned into becoming a professional engineer in due course. And to do that, our mission is to convey our experience and our knowledge to at least to 100,000 future professionals out there through our online courses. The good and main advantage about is you can study at your own pace, at your own time, anywhere you are, and that's the key. So you don't have to go to a face-to-face class and spend hours in sitting and learning, whereas you can pause your day study, you can go back and learn again on your own pace. So that's really good about it. A little bit about me. I'm Arul Prakash Anbukarsu. You can call me as Aru or IPA, as popularly as I would like to be. I have 20 plus years of experience working in various industries in Australia. I came to Australia back in 2003 to do my master's degree majoring in embedded systems, VLSI and project management. Since then, I've been working in these industries, majoring on renewable energy sector that majors in energy confirmation from solar and wind, power systems, lead acid batteries, and network embedded systems that related with the automatic teller machines, the teller cash registers, point of sales, banking automation systems, and smart parking operations. So these are my expertise on these three embedded systems, VLSI, and project management. So that's why I feel like it's about time I could share my experience and knowledge to you all out there, so you can also shape up to be like a real good professional engineer. And almost I have went through the whole embedded development life cycle, as you would have learned from day one session. So that's why I have the in-depth experience working in all the different departments. So I would like to give that value to you, so you will also get the insights about how each and everything works. But due to on popular demand and through my mentor's recommendation, we are releasing this course for you to get started, because this is a really interesting microcontroller and the go-to microcontroller that every engineer would prefer to use in their projects. So that's why we are here, and we are on day 12. So let's get in and see what it is about today. A little announcement to make before I get into the concepts. I categorized into two different categories. One is a YouTube viewer, and the second is the internship professionals. I'm going to download, or I have already been downloading all the video sessions into my YouTube channel on A2DG. If you go there, you can view the YouTube viewers. You can go there and watch our videos. In order to be eligible to get a free certificate, you have to attend at least 25 to 28 classes, so that you will be eligible to get a free certificate. A small drawback is due to YouTube regulations, the videos can't live there forever, so it has to be removed after 2 or 3 days. So if you miss a day session and if you want to go back and revise, you would get missed out. So that's a small drawback. You have to make sure you log in every day and learn from the watching the YouTube. So that's why I strongly recommend you and advise you to join our internship program. And what would that achieve is to acquire you an internship certificate. I told you this before and I'm telling you again, that's worth a lot. So when you get into that first job, when you work with your senior engineers and your product managers, your other managers, they value that your 30 days of involvement in knowing microcontroller, and you got tons of experience to their mind, because as a fresher, when you land in, it's very hard to get your head around to know a lot of concepts, because in the industry they are super busy and they won't have much time to explain basic things, fundamental things. And so that's why they consider this as a really big asset for them, for their team. So that's why learning through our internship program, you'll get that experience as well. Not only that, you get to have your own sign-in login, so you can go into our learning management system portal and you can go through each and every session. And once you complete and continue, that counts for your attendance link for the internship certificate. And on top of that, you will also get to access to all our course contents unlimited. So that's for rest of your professional career. Whenever you want, you can go back and you can watch it over and over and again. And also the access to the course content videos. You can actually pause and you can come back, you can rewind and forward your videos and watch it. So you got unlimited access to all of those, and all the course contents, all the PDF materials, the source codes, and all the necessary documents that goes with the learnings. And if you get stuck somewhere, please contact our backend support. They are a very friendly mob, and they will be able to help you to make you move further along to learn. So let's get into it. These are all the materials you would like to acquire, and I'm sure most of you would have got it by now. If not, please contact Pantex Solutions. They are a big manufacturing company, and they would be able to assist you and help you to acquire you all of this. And so I keep saying, you don't have to use this and think that, that's a waste of money. You can use those materials and you can build your own projects and you can build your own design. So it doesn't stop here. You can also do it in your other projects as well. So it is well worth money spent. So please do purchase that. And the more you practice yourself, the more hands-on you get onto those materials, the more knowledge you gain. So that counts a lot. So please go ahead and buy all these materials. So, shall we start to learn about the linker scripts for today? I am keen to teach you today, so let's get in and get ourselves started to learn. Today, we're going to learn about linker. What is a linker? As most of you would have learned through your engineering days, that when you write a program, this is one of the concepts that many of your professors would have taught you already. If not, I'm giving a small recap. A linker is an important utility program that takes the object files that's been compiled and linked through the compiler. It produces by the assembler and the compiler and the other codes to join them into a single executable files. In other words, when you write the program, when you hit the build project, the compiler gets that project and then converts to the object file, and the object file is sent to the linker file with the assembly language, everything in it, and then it comes out as a final executable file. So that's where the linker comes in handy. The linker's main role is to give absolute addresses to all these object files. So when it comes out from the .o, it doesn't have any address. So the linker's main job is to give addresses of that so that it can be downloaded and used in the microcontroller. So that's the part of the linker. And by doing so, you got a different executable formats. So what are all the linker outputs? The linker outputs come in a few different formats, like as you can see here. One is an executable image format. The output is the ELF shared object. The other is the partially linked ELF object, and it's a relocatable ELF object. Again, the ELF stands for executable link format. So when you combine that the compiled program to the linker, the linker scripts plays in its role, where it declares its memory declarations and the sections, as we previously learned about in the startup file, that how you create your own sections. So likewise, the linker script will declare its own memory, where that is going to be placed inside the microcontroller memory, whether it is in the flash memory or it is in the SRAM memory. And also it will declare its sections, the start address and the end address, or where it has to be located. So that's where the linker will come in handy. And the basic structure of the memory will have all the initialized and uninitialized data in flash and RAM, SRAM. So the sections will cover available what's in your project. So if you write your program, and the section will tell you all about from that project, from that code. But as you learned from yesterday, you can also customize the section by writing your own ISR vector that you learned from the previous session. You can also write your linker scripts, like after by the end of this session, you will have a better understanding to write your own linker. And so the linker file, what it does is it customizes the section to a particular memory, and it links by mapping those to the object files and putting the address to that object files, and it maps it, groups together, and links to use it as an executable format. As you already know, the linker script is comes out as a text file, so that's why you downloaded that GNU toolchain from the previous session, and that will give you all the necessary files that you may be able to, if you want to use in command prompt, you can use arm-none-eabi-gcc.exe, that's to execute for compilation. Likewise, if you want to use the link files, then the option in command prompt is, by memory, for compilation we used -c or -c. For linking, it's the -t, lowercase t. So that will help you to link the object files into the executable files. That's the linker's job. By default, STM generates its own linker files that I will show you as we move along with this learning. If not, after you go through this, you will be able to write your own linker scripts, and that's even it's easier to do in that way. So I'll show you how the linker project. So this is the structure. This is the structure of a linker file, as you would have realized from day 3 or 4. This is the how or what is inside the linker file. It will have a linker.command, and in the linker command it will have the hardware memory description and the software sections. The hardware memory description will have the name of that memory description, its location, its length. Example, IRAM origin and its length. In our example that I'm going to show you, you would see the flash and the SRAM and its origin and its length, how much space it's going to occupy. In STM32, we have a built-in 128 kilobyte flash and 512 byte of RAM in it. So, and also the software sections, it will have the name of the section and it will have the memory area linked to that particular memory allocation. So linker, as we learned, is gets the object files and it maps with the addresses and comes out as a final executable output. So that's the linker's job. I'll show you in an example. You will get better understanding. So I already opened IDE and I'm going to use the example for blinking LED. So .ld, that's the linker script. So by STM32 generates both the flash linker. LD is the extension for the linker script, and both the flash and the RAM. So the LD, as you know, these are all the for references that you have to write what that file is and who wrote that program, and you have to give a little bit of introduction about which board you are going to write. This is all for anyone, like for a program manager or a project manager may not have an understanding, so he has to budget himself, so he has to know which one you are going in your project, so he can allocate the budget for you. So that's why you need to give little bit details about what board you are using and what is the memory that it has. Sometimes you have to buy external memory to use in your project, so that's where the budget comes in. So you got to tell them this is what it's all about. So don't worry about this green bit. It's slash and in asterisk, and that's almost like the comment section. So these are all the the memory definition that will be. I will go through each and every line later, but I'm just giving you a short introduction about what it is. So the LD description, the linker description, will come with a memory name, and it will show its origin, where it's going to start, the start address, and its capacity, its size, 128 kilobytes and 512. This is how the linker file will start defining its memories. Okay. So now let's understand a little bit about what is linker scripts. The linker script, as I just told you already, I covered all of this, but I'm just giving a recap. Linker script is a text file which explains how different sections of the object files should be merged to create an output file. There will be different, in multiple projects, there will be different object files. So the linker is the one which collects and gathers all those lookalike. For example, if it has got .text files, .data, .bss, so it has to gather all of that and then bundles together, groups together, and puts into one single output file and the same name. So that's the linker script. The linker scripts are written in GNU linker command language, and the file extension that's used is .ld. The linker script also includes the instructions and data memory addresses and its size information. As we just saw, the memory definition, it will have the memory name and the address and the size. So those are all will be described in the linker script. The linker and locator combination assigns unique absolute addresses to different sections of the output file by referring to address information mentioned in the linker script. So the object files that comes in won't have any addresses. The linker and the locator will issue two absolute addresses to the object files, and that's what linker does. So you must apply linker script at the linking phase to the linker using the T option, which is done in the IDE. And this is what we just saw. In STM32 Cube IDE, if you want to execute mainly for debugging, then the RAM is used for ram.ld, linker description is used for debugging, but the main linker description is written for the program memory, where your program memory stays. That's the flash memory, so you could use a second linker that places in RAM memory only. And these are all the linker script commands that's used in the linker scripts. What is it? The entry script command, then followed by the entry is the memory script command. Then there are sections. As you already learned yesterday, there are different sections in the startup file. So similarly, you will see those sections here like .text, .data, .bss, .arm attributes, .rw data. Likewise, there are sections, and then you're going to learn about what keep script command will do, and what is align command will do, and what is at greater than symbol will do. So we'll see that shortly one by one. And first we'll get into learning about what is entry command. This command is used to set the entry point address to tell the microcontroller from the linker description where the start point address is, where it starts in the header of the final ELF file. In our case, the reset handler is the entry point into an application, the first piece of code that executes after the process resets. So the entry command is nothing but once you press the board. I just connected my my board. I'll just show you. I have connected my board, as you can see. It's connected to my computer, so that's where I generated the LD files, the linker description files. I went ahead and I just did the build project. So in our case, we are saying when you press the reset button on the board, on this board, when you press the black button, the reset button, it starts and lets the programmer knows that reset button is pressed. So therefore, from the entry point, it has to go to the reset start. So, oops, sorry, I'll fix it. Reset point. So the debugger uses the information to locate the first function to execute, and it is not a mandatory command to use, but required when you debug the ELF file using the debugger gdb. The syntax for the entry command is .entry underscore symbol underscore name and then entry reset of handler. I'll show this in the IDE with the program, so you can understand a bit more about it. So this is the Day12 blink LED, the STM32 generated itself. So this is the reference that we don't have to worry, but it's a good practice that if you start to write and follow this, and being working in multiple project, and this little piece of information comes in handy to locate for files. So the entry point we just learned, the first command, it's entry, and we are saying what its name is. So we're going to ask the controller to go to reset handler, and inside the reset handler we already know what the reset handler is used for and what its purpose. Its name is eStack, and this is all symbols. You will learn about that underscore eStack, and it gives the origin, the start address, and also it gives the length, the end of the RAM type. And also it will have the heap and the stack sizes. For example, if you want to blink the LED and store the data in your memory allocations, you need to give the address allocation. So 0 by 200 or 0 by 400, the heap and the stack sizes. But for example, if you are working on a image processing projects, for instance, you need to consider a lot of coefficients, and where you're dealing with plenty of data to analyze. In that case, 0 cross 200 and 0 cross 400 may not be sufficient, so in that case it will throw an error. It could be a controller bouncing data error, so in that case you need to increase your heap size and stack size. So it has to be checked with what applications that you are using, and you can also modify here as well. So that's the entry point, and then the eStack will let you to do that reset handler. Then comes the memory definition. How you define the memory that you're going to use this. So I'll show this here, and then I'll come back here. So far we learned about the entry command and then the reset handler. So the next command we're going to learn here is the memory command. The memory command allows you to describe the different memories present in the target. Here we are learning in this series is STM32F411, so it has both flash and SRAM memory, and that's the target start address and its size information in the memory definition you just saw. One linker script will have one memory command. At least it will. The reason to put that point there is it will have at least one command to show where the memory is. So the linker uses the information mentioned in this command to assign addresses to the merged sections. So as I said, the linker is the one which takes the object files and throws addresses to merge sections. So that's what the memory command does. The information is given under this command helps the linker to calculate the total code and memory consumed so far without any error. So that's where the image processing example I given, if considering large number of data, then you have to adjust the heap and the stack sizes so that it can be fit and available to store your data in that. So by using memory command, you can fine tune various memories available in your target and also allocate different sections to occupy different memory areas. And this is how you write yourselves. Like if you want to write your own memory definitions in your project, and this is the syntax you got to use. Always the command names should be in capital letters, meaning uppercase. It can't be written in lowercase because it will throw an error, and that's how the manufacturers program that way. So it has to be in memory, and then open braces followed by close braces, then the name of the memory. If you're working on the flash memory or the RAM memory, you have to give the name, and everything should end with the colon, so that's important. And then the origin is the starting address of that memory, so you need to give that origin, comma, the length, the capacity, the space of that name, and then close the bracket. So you're going to tell the one in STM32F411 we are having 1024 bytes of flash and 128 kilobytes of SRAM that we are using. And to write the definition, this is how you write memory in RAM XRW. What are these XRW? The XRW is nothing but it's a attribute to say what that memory allocation or what that memory is supposed to do. For example, for an X, it is a section containing executable code. Yes, you can also save your program code and you can start to run your program from the RAM memory itself. In case of if there is not sufficient memory in the flash, you can also use to store that in your RAM as well. R stands for read-only sections and W stands for read-write sections. So that's what it mentioned. RAM, it can be read and writable, so that's why rewritable and executable, and that's what XRW denotes. Whereas in flash, as you know, it's only a read-only memory ROM. You can only read and you can execute it. So that origin location is 0 cross 8 000, and its length is 512. That's a flash memory. So this is how you have to write your own memory command, and you saw that in the project itself, the project that we started. So that's a memory definition, RAM, XRW, origin, that's the length, and the flash, RX, read only, and executable. Its origin, that's a starting address, and its length. So that's the memory definition. Okay, so let's move into learning about the next command. The next command is sections command. As you learn from starter file as well, there are few different sections. How it gets that from your derived program, that you write your command, the compiler pulls data, collects all the information, and then groups itself into categories of sections. So the section command is used to create different output sections in the executable generated file. The important command by which you can instruct the linker how to merge the input section to yield an output section. So that's where the sections come in handy, where the input is coming and how you can get the output. This command also controls the order in which different output sections to be stored in the vector placement tables, as you learned. The first one will be the main stack pointer, then the data, then the .bss, .text, and etc. so forth. It will be there. This command. By using this command, you also mention the placement I just said of a section in a memory region. For example, if you instruct the linker to place a .text section in the flash memory described in the memory command. So now let's understand a little bit about the linker and the locator. As I said, what the linker does, it takes the object files from the compilation projects and it groups together all the likely names of the projects, and then it comes up with the final executable file. In this example, the main.o and led.o will have all these sections, .text, .data, .bss, .read only data. So it has to group .text from main.o and it has to group .text from led.o and merge into one single file as .text, and it will be ready to gather everything like that. So .data is grouped like that, .bss grouped like that, .read only data grouped like that, and then comes out as one final executable file. This is just an example just to show you. This has a main program, it has got swap off. The system code, this is object code is a relocatable code, and this is the relocatable object files that comes after the first compilation from here, and then this is the final ELF as the executable object file, where it places everything in the memory locations with the addresses and how it's all folded and how the .text and .data is grouped. So this is just to give a small example how that final allocation is done. Okay, we learned about the sections just briefly about what they all do, and this is the syntax you got to follow. As you learn from memory command, all the command sections, the name should be always in uppercase, capitals. Sections, everything will start with the open curly brace and close curly brace, and .text, you have to start everything with .text. Dot is important. So open the braces and merge all ISR vectors of all input files and merge all text section of all input files. And then you got to use the add command to have VMA and LMA. I'll tell you shortly about what they are. And then you have to group the next section as .data. You have to merge all .data section of input files. And again, I'll show you what VMAT and IMAT. So this is how you have to group yourselves to write your sections. So if you go into the project, the next section is after memory, you're going to write these sections. The previous session, you written yourself to generate your own section ISR underscore vector. The STM32 will generate that by default, and this is the one we just learned. Open braces, .isr is a section name, and it gives with the dot and align of 4. Align you will just learn shortly, but this is a section. This is how you have to declare for the startup code to run. And then once you say how you're going to align, then you need to group that into various sections as .text and dot RO data, etc. Excuse me. And dot arm external tab, exception tab, sorry, dot arm, and likewise. So these are all the different sections that included in the program sections. The storing a final executable file, this you learned already. So the RAM, the startup file, gets the responsibility to move all the data from data from flash to memory, just for one major reason, because the flash memory is only read-only memory, where you can't modify data files. Like if you want to modify the variables, you can't do it. For that main reason, you need to copy all that from flash file, and you have to allocate some space in the RAM, and then you copy that, and that's how the startup file plays the major role. So that's what we learned last session, and this session, how that allocation is done and how it's linked to the addresses. So as you learn from the other session, everything has to have the ending address and the start address. So the data will have the end address e text and the start address of data. So all these three are important. What is LMA and VMA? As you saw in the other project, it has written after you write the section, and you need to specify where that section has to be placed, whether in the flash memory or in SRAM memory. So that's where, if it is flashed in the if it is placed in the flash memory, then it's called load memory access. So it's actually loaded into that flash. But if you load that into a SRAM memory location, that's called VMA, virtual memory access, because it's not inside, it's outside the program memory. So that's what virtual means. So the LMA is the load memory address, is the address to which the section will be loaded. In many cases, both VMA and LMA could be the same, but in some cases the data section is loaded into ROM, that's the LMA, during the flashing process. Whenever the program starts, the data section is copied to VMA, that's the RAM. I'll show you a little example, the RAM and ROM. So we are in LD section. So if you go to Window, Show View, and you go to Build Analyzer, sorry, I'll compile the program first. I'll show you this. Compile now. Because I connected the board, I'm going to debug this as the STM32 application. We already did this setup, so okay. So now we have to go Window, and I'll show you the build analyzer. Okay. And this is the build analyzer, as you can see. I'll expand this so you'll know. Now this is the build analyzer, as we learned about the memory definition. So you have both the RAM and the flash memory. It will have both the start address and the end address of that particular RAM and particular flash. Has a built-in, going to switch, yeah, okay, 128 kilobytes, 512 bytes, and it shows how much the usage is. Sorry, you have to just wait. Okay, we are in debug mode. So Window, Show View, we're going to see the analyzer. So we were describing about learning about the memory section. So that's the free space and how much it's totally used. If we go into memory details, this is what we are learning now. So inside the memory details, the flash memory .isr vector, yesterday you learned about, or the previous session you learned about ISR vector. So this is how the sections are grouped here, .text, .rwa data, and different, you learn about this. and inside the RAM how it is all merged and grouped together .data.bss. So this is how it's done in the program. Um, sorry, I got to show you LMA and VMA, and this is in memory details. Okay. And we just learned about LMA and VMA theoretically, and I'll show where that actually is. So if you click on the memory details, as you can see, the run address, wherever that data is stored in the memory locations, if it is in RAM, it will be a virtual memory address, and if it is in flash, it will be, sometimes it can be both, but as you can see, both the addresses inside the flash will be the same address. So that's why it's called load memory address, and this is a virtual memory address. So this is the difference between LMA and VMA. LMA is load memory address that's situated in flash, and VMA is virtual memory address that's situated and live in RAM. I think maybe we are going a little bit longer, so I'll just give you that breather. So go and get that break that you all waiting for. Go and grab yourself something to drink and have a bite to eat, and I'll catch you in a couple of minutes. So see you shortly. See you then.